Hi, for my presentation, my project is titled Flexible Temperature Sensor for Body Temperature Monitoring. With the post-pandemic of COVID-19 that occurred globally, a restrict and new normal of standard of operation (SOP) must be followed in avoidance of spreading the disease, especially the body temperature checking that lead to main symptom of having COVID-19. The body temperature monitoring system can help to reduce the cost of healthcare by forecasting disease risk and can improve the quality of life and safety of the people by helping to manage existing conditions. With a wearable temperature monitoring device, the healthcare technology will once again rise with more features that help the people monitoring their health more efficient. It is very important to have a high sensitivity and stretchability sensor so it can measure a very wide range of temperature within its resistance. However, the resistive sensor could have low deformation resistance and stability when measuring the temperature on surface with different curvatures. The thesis explored the development of flexible resistive temperature sensor by using carbon nanotube (CNT) and print onto the flexible substrate which is Kapton HN film. Few design of serpentine structure were designed with specification to achieve high sensitivity of sensor. The result obtained from LabVIEW show the performance of sensors in aspect of linearity, sensitivity, and time response. The aim for this project is to develop a sensitive, flexible body temperature sensor. Thus, the research objectives include to design multiple specifications of resistive temperature sensor to investigate the performance of sensor. Next, to fabricate the resistive temperature sensor onto the flexible substrate using screen printing technology. Lastly, to characterize the flexible temperature sensor such as linearity, sensitivity, and response time. For methodology, the project starts with designing layout of sensor with variable length and width to characterize the performance, such as the resistance change when variable set of temperature applied in the experimental. Then the sensing material carbon nanotube (CNT) and the electrode material silver conductive paste is prepared. Thick film technology is used to print electrode and sensing layer on flexible substrate, which is Kapton HN film. Following that, the printed layer will be burned at specific temperature to facilitate drying. IV testing will be performed on the printed sensor for characterization. The data from the characterization will be collected for research purposes. In design specification, this sensor were designed with four various length, which is 16 mm, 24 mm, 32 mm, and 40 mm, which classified as design A, B, C, and D respectively. These four designs are varied with a secondary remainder length B of 8.5 mm and 16 mm for more accessible data collection as shown in Figure 2, which comprising a total of 8 design. Table 1 is the reference for specification of design in Figure 2. Based on the specification table, the primary render length A, width and thickness is constant with value of 3 mm, 1 mm, and 1 mm respectively. For fabrication part, the sensor will be constructed utilizing the screen printing method to ensure that the substrate is stable throughout the printing process. The Kapton HN film is taped onto the board. After that, the mask is covered with the carbon nanotube paste. The paste is then forced through the mask and onto the substrate using a squeegee. All printed sensors are thermally cured in a furnace for a specific amount of time and temperature as shown in Figure 3D. The process is repeated after applying the silver paste for electrode onto the sensor. After the thermal curing process, the sensor is cut and ready to be tested. In result and discussion, a few parameters of sensor are recorded. The parameters such as IV linearity, resistance value over temperature change, time response, and sensitivity. In sensing parameter, the linearity of the sensor play a crucial part. The linearity of sensor can be defined as the closeness of the calibration to a specific straight line as shown by each sensor in the figure. In IV characterization of resistance, the value of current is proportional to the value of voltage, resulting the linearity of the sensor. For the next result, the resistance record is the resistance with voltage supply of 5 volt over the temperature of 25 degrees Celsius to 41 degrees Celsius. From the data, the design B1 are having deformation as the temperatures change from 39 degrees Celsius to 41 degrees Celsius. The data collected during 41 degrees Celsius is exceeding the normal value of 1.19 megaohm, which generating thrice the value of resistance from temperature of 39 degrees Celsius, which is 44 kilo ohms. The resistance value of design A1, B1, and C1 was quite visibly decreased respectively with the increase in temperature. Since CNT is a nano powder, the observed resistance to temperature connection may be explained by increase in charge carrier concentration in CNT film, similarly to how this occurs in semiconductor. Time response of the resistive sensor can be obtained by how much the time taken for the resistive value were taken. In this project, the value of resistance is taken average of 10 seconds for 5 volt of voltage supply at the temperature of 35 degrees Celsius. The, the time response of all design is 1 second to detect the resistance change. The temperature coefficient of resistance, often known as the alpha constant, represents the resistance change factor per degree of temperature change. Just as every material has a unique resistance, so too does the resistance vary slightly with temperature. This coefficient is negative for the elements such as carbon, silicon, and germanium, indicating that the resistance reduces as temperature rise. Some metal alloy have temperature coefficient of resistance that are almost exactly zero, implying that the temperature change have very little effect on the resistance. Thus, from the graph above, the design A2 has the highest sensitivity followed by design B1 and A1. In summary, the design, develop, and testing for resistive temperature sensor were done successfully. The sensor's resistance, sensitivity, and time response were examined. The comparative results show that the design A2 and B1 are the most functioning with the highest sensitivity and smoothly decreasing resistance during the temperature rise. The design of resistive sensor will determine the performance of its measurement, thus conclude that design with similar dimension than B2 is more preferable. That's all. Thank you.